Good morning everyone. Myself N.Uday Ranjan Goud, working as Assistant Professor in Aeronautical Department, MLR Institute of Technology. So in the last session, we have seen the introduction to thin plates, and we have also seen how thin plates are being classified as thin, thick and membrane forces, and we have also seen the thin plate application also. And we have seen there are wide range of applications for the thin plate, that it may be used in marine engineering, it may be used in ocean engineering, it may be used for automobile engineering, etc., along with the aerospace engineering. So now here, after seeing the thin plates introduction, now we will have to extend our analysis like how thin plates behave when they subjected to different types of loading. So in that, the first one we will see the bending effect. Okay, so bending. So we know that whenever the force are applied on any particular beam, then the beam is subjected to bending. So now here I'll recall the previous semester that when you studied in solid mechanics or when you studied in strength of materials, what we used to do is we used to consider a normal element, rectangular element, and then we apply the end moments, that is capital M here. And because of that, we derive a relationship for bending, which is nothing but M by I equals to sigma by y equals to E by R. So this is called as bending formula, in which capital M is the bending moment, I is the moment of inertia, sigma is the direct stress due to bending, and y is the distance from neutral axis. E is the Young's modulus of the material, and then R is the radius of curvature. So we derived here. Now here we just assumed equal moments are applied on the ends of a element what we considered. Okay, now here we are going to extend our analysis further little, that here since we are considering thin plates, instead of applying M, now we assume moments capital Mx and capital My are the moments. So Mx and My are called as bending moments applied in X plane and Y plane. So instead of using one moment, now here we are going to use two moments, that are Mx and My in the analysis. Now because of these moments which are applied on the thin plate, we will see how the thin plate behave, and probably will try to derive the relationship for bending of the plates. Okay, so now here, now it comes to pure bending. Now this is very, very important, pure bending. So pure bending is nothing but we are going to apply only bending moments. Now that means we are neglecting the effect of shear. We are not considering shear, only pure bending. And in the case of pure bending, we will apply only the two moments, that is Mx and My per unit length. Now let us assume a thin rectangular plate as shown in the figure here. So you can see here Mx and Mx bending moment is applied on the two edges, in which you can consider the cross sectional dimensions. This is A and this is B, A cross B, and Mx is applied on the two edges here. Okay, and you can see the another moment My per unit length is applied on other two edges. So when these moments act simultaneously, we need to see the effect of these moments. And you can see thin plate, and you can see x-axis system, y-axis system and z-axis system, and in which we consider the thickness, that you can take any of this one. This is nothing but the thickness of the plate. So when you compare the lateral dimensions A, B, the thickness is very small. So that's what we will consider this kind of plates as thin plates. So now here the former bending moments are applied along the edges parallel to the y-axis, the latter along the edges parallel to the x-axis. So what we need to see is Mx is applied parallel to x-axis and My is applied parallel to y-axis. That is what we have to see from this diagram. Okay, now let's consider an element of plate, a side delta x delta y. Now that is the thin plate we have seen. Now let's consider a small element in that thin plate, and let us assume the edges of that plate as elemental plate as delta x and delta y, and having a depth equal to thickness T of the plate. We are going to see the figure also. And suppose that, let us assume the radius of curvature or radii of curvature in along x and y plane. Let's consider them as rho x and rho y along xz planes and yz planes, and positive curvature of the plate corresponds to positive bending moments, which produces displacements in the positive direction of the z or in the downward axis. Now let's see these elements in the diagrammatical manner. Now this is the element what we considered. Now you can see here we considered element in which we consider the sides as delta x, delta y. So for analysis, this diagram is very important because we are going to draw or we are going to write the equations from the diagram itself. So it's very important to clearly understand this diagram because of element that is there and how we are considering the plate dimensions, how we are considering element, neutral axis, how we are going to consider the stresses and all we have to observe in this diagram, and this is very important. Now, so a rectangular, a small element we considered, and that we are making it as magnified element and we are showing here. And now here let us assume the central element A element as neutral axis or neutral layer, about which there is not going to be any kind of tension or compression. Now from the neutral axis, let us assume a distance of z, and we considered and again a small element along the length of the plate like this. Okay. Now let us assume the width of this one is delta z. Now there are the stresses that are represented over here on this edge BC, and we have represented the stresses, that is nothing but what? Sigma x. Okay. Now here sigma x is the direct stress that is induced because of when you apply bending moment mx. Similarly, sigma y is induced because of the bending moment that is applied my. Okay. Even other two edges also there, but when we are looking from the front view we are unable to see, but even on the other two edges also mx and my will be induced. So now let us assume the thickness of the plate as t by 2, and from the neutral axis we can see above of the neutral axis it is plus t by 2 and below of the axis it is minus t by 2. Now this is very important. So now we considered one element and in which we represent the stresses sigma x and sigma z, and we have also assumed that the elemental thickness or elemental width that we considered is delta z. Okay. Now let's visualize a thin plate, a normal thin plate. Now when you apply the bending moments, for example, if you consider one thin plate like this, now when you apply mx like this, it's going to take curvature, right? Now that curvature is shown with respect to some reference point. That curvature is designated as rho x. Similarly, and when the other two bending moment, that is my, is applied on the other two edges, again it is going to take the curvature, right? So that curvature is represented by rho y. Now this diagram B indicates that rho x and rho y are the two curvatures that we are going to get when you apply bending moments mx and my on the thin plate. And you can see another one, that is n, which is nothing but what? Neutral axis. And we know very well that neutral axis, along the neutral axis there is not going to be any changes along that line. So that is neither that layer subjected to compression nor it is subjected to tension. So that is the reason it is called as neutral layer, and all such layers passing through an axis is called as neutral axis. Now by considering the first diagram, that is figure A, we are going to develop some relationships for strain, and then we write stress, and then we probably write to extend this derivation. So from the diagram we have seen, and then now we are going to write the expressions for direct strains, that is epsilon x and epsilon y, corresponding to sigma x and sigma y of an elemental lamina of thickness delta z at a distance z below the neutral plane, and those are given by the simple normal strain conditions, that is strain is nothing but that is equals to z by rho x, and where z is a distance from the neutral axis and rho x is the curvature, and strain in y direction is given by z by rho y. So let us assume this as equation 1. Okay. And now we already know that the stress strain relationships, right? The strain in x direction and strain in y direction and strain in z direction. Now what are those relations? Now when you see epsilon x equals to 1 by E into sigma x minus nu into sigma y plus sigma z. So in which the sigma z is the stress in the third direction, that is z direction. which you can assume it as 0 because we are considering thin plate in which only will have two dimensions, sigma x and sigma y, and you can rewrite this equation. So you get epsilon x equals to 1 by E sigma x minus nu into sigma y. And similarly, you can write sigma y as well, epsilon y as well. So epsilon y, that is equals to 1 by E into sigma y minus nu into sigma x. Now what we can consider is, by considering these two equations, that is equation 1 and equation 2, we are going to substitute epsilon x in place of here, substituting for epsilon x and epsilon y from first equation and rearranging into the second equation and rearranging the terms. Now when you substitute epsilon x and epsilon y in the second equation and when you rearrange the terms, you are going to get the expressions for sigma x and sigma y. So you are going to get sigma x, that is equal to Ez divided by 1 minus nu square into 1 by rho x plus nu by rho y. Similarly, you are going to get expression for sigma y, that is equal to Ez divided by 1 minus nu square into 1 by rho x plus nu by rho y. Okay, here we are using nu, that is nu is nothing but the Poisson's ratio. So now let us assume these two equations together as equation 3. Now let's extend this analysis. Now, so we have one assumption we've seen in the previous session also in the thin plates assumptions, that plane sections remain plane even after bending. So whenever we consider this assumption, plane sections remain plane, direct stresses vary linearly across the thickness of the plate and therefore their magnitudes depend on the curvatures of the plate. In other words, their magnitudes depends on the bending moments of the plate. Now we have an equilibrium condition. Since we are applying bending moments mx, my and stresses are going to induce sigma x and sigma y. So we'll have one relationship, equilibrium relationship between these two. So that is nothing but the internal direct stress distribution on each vertical surface of the element must be in equilibrium with the applied moments. Okay, so what is that? The internal direct stress distribution, that is the moment due to sigma x or sigma y, this should be equal to the applied moment, that is mx and my. Okay, so here we need to consider the equilibrium because of these two, applied bending moments and direct stress distribution. Now we are going to write that equilibrium equation, that is applied bending moments must be in equilibrium with the internal direct stress distribution that is developed on each vertical surface of the element. Okay, so we are going to write that derivation. So now when we write that, so left side is we are writing the moment equilibrium. So as we assume bending moment mx per unit length, we have to multiply with the length on which it is acting to convert into moment. So mx, and we can see in the previous diagram, so mx is applied on this edge, and as we know that when we consider the edge lengths, this is delta y edge and this is delta x. So mx should be multiplied with delta y so that it will be converted into moment, as we assume mx as mx per unit length. So we have to write mx into delta y. Now it becomes what? Moment. Similarly, when we see my on the other edge, my into delta x becomes moment. Okay, by multiplying with respect to length on which it is acting. Okay, so now going back to this derivation, so we have to write mx into delta y and then mx my into delta x. So these are the applied bending moments because of the mx and my to the left side of the equilibrium equation. Now the right side we need to write because of the stresses. Now as we know that direct stress, there is a relationship between stress and force. So stress, when you multiply with the area, it becomes force. So similarly, sigma y when become multiplied with the area, it becomes force. Now since we are writing moment, so these two together is nothing but force. Now we need another perpendicular distance. Now that another perpendicular distance we can consider it as z. Similarly here also perpendicular distance is z. So stress multiplied by area and it's going to get force, and then when it's multiplied by perpendicular distance, now together you can consider it as moment. Okay, so now in this fashion we are going to write, and area, what we are going to write is the area of the element. Okay, so area of the element. Now let's go back and see how we can write area of the element. Now if you look at this element, this area, so this is the delta YH and we are considering the thickness as delta Z. So area for this element is delta Y and delta Z we can consider. Similarly, when you consider the horizontal strip here, this length is delta X, elemental length, and then thickness is delta Z. So for this case, you can write area as delta X into delta Z. Now this is what we are going to reply. So for the first case, first equilibrium equation, we are going to write area as delta Y, delta Z. And for the second equation, we are going to write area as delta X and delta Z. So with this, we are going to replace in this place A, we are going to write delta X and delta Z. So delta Y and delta Z. In this case, we are going to write delta X and delta Z. So with these changes, we are going to write the equilibrium equation. That is, the applied bending moments must be in equilibrium with the internal direct stress distribution on each vertical surface of the element. Okay. So with these changes, we are going to write. So we are going to write the left side, that is mx into delta y, and right side, that is nothing but what? Sigma x is the stress, and when you multiply with the area dy into dz, these two together becomes force, and the perpendicular distance is nothing but what? Z. So with this, we are going to write the element. So since we are writing for the element, and if you want to write for the complete element, we can integrate it from the lower surface to upper surface, that is from minus t by 2 to plus t by 2. So mx into delta y, that is equal to sigma x into dy dz into z. Now it becomes the moment, and then we are taking the limits of integration, that is minus t by 2 to plus t by 2. Similarly, we are going to write another equation, that is my into delta x, that is equal to sigma y is the stress multiplied with the area dx dz, then it becomes what? Force, and the perpendicular distance is nothing but what? Z. So in this like this, we are going to write bending moments equilibrium along with the internal direct stress distribution. Now once we get this one mx, now from both of this equation, delta y gets cancelled, and we are going to write mx equal to integral minus t by 2 to plus t by 2 sigma x into z into dz. Similarly, my, that is equal to minus integral minus t by 2 to plus t by 2 sigma y into z into dz. Now in these two equations, we are going to substitute for what is sigma x and sigma y from the previous third equation. Now what are the sigma x and sigma y? When you go back and see, sigma x and sigma y are these two equations. So we consider this as third equation, this as second equation, and this as first equation, right? So sigma x and sigma y, that is nothing but third equation. Now we are going to replace this equation 3. We are taking equation 3 and substituting in the next equation, which is nothing but here. In place of sigma x, we are going to substitute that equation number 3. In place of sigma y, we are going to substitute that equation number 3, and we are going to rewrite that equation. Then we are going to get mx, that is equal to integral minus t by 2 to plus t by 2 ez square by 1 minus nu square into 1 by rho x plus nu by rho y into dz. Similarly, my also you are going to get integral minus t by 2 to plus t by 2 ez square by 1 minus nu square 1 by rho y plus nu by rho x into dz. So this you can assume it as fourth equation. Now we got an expression for mx and my. The next what we are doing here, we are assuming capital D as D is nothing but flexural rigidity. D is nothing but flexural rigidity, and which is nothing but D is the product of capital E and I, Young's modulus and moment of inertia. So for this thin plate, and what we are considering here it as whatever we have here, integral minus t by 2 plus t by 2 ez square by 1 minus nu square. Now we are assuming this as capital D, okay, and we are replacing this in both of the equations as capital D and rewriting these equations. So when you do that, we are going to get D equals to minus integral minus t by 2 to plus t by 2 ez square by 1 minus nu square into dz, and when you integrate this between the limits minus t by 2 to plus t by 2, you are going to get et cube by 12 into 1 minus nu square. Now when you replace and write, you are going to get another set of equations. Let us assume this equation as capital D, flexural rigidity, as 5, and when you replace D and rewrite the previous equation, we are going to get mx equal to D into 1 by rho x plus nu by rho y, my equals to d into 1 by rho y plus nu by rho x. So these equations also important that you have to remember. Okay, so where d is nothing but we call it as flexural rigidity of the plate, which is nothing but the product of Young's modulus and moment of inertia. Now coming to the deflection, for example, if W is a deflection of any point on the plane in the z direction, then we may relate W to the curvature of the plate in the similar manner from the well-known expression of beam curvature. We can write this as 1 by rho x, the curvature, is equal to minus dou square W by dou x square, and 1 by rho y is equal to minus dou square W by dou y square. So now here we are going to replace the rho x, 1 by rho x and 1 by rho y, what we have in terms of the deflection, that is minus dou square W by dou x square minus dou square W by dou y square, into the previous equation, that is equation number 6, and then we are going to rewrite this equation. So we are going to write here 1 by rho x, that is equals to minus dou square W by dou x square, and then 1 by rho y, that is equals to minus dou square W by dou y square. Now these two we are going to take, and then we are going to replace, substitute in place of 1 by rho x and 1 by rho y, and then we are going to rewrite that equation. So when you rewrite that equation, you are going to get mx is equals to minus d of dou square W by dou x square plus nu into dou square W by dou y square, and my we are going to get minus d into dou square W by dou y square plus nu into dou square W by dou x square. So this equation, you can consider these two equations as equation number 7. Okay. So what we need to understand here, it is mx and my, these two, equation number 6 is written in terms of the curvatures, that is rho x and rho y. Similarly, mx and my can be written in terms of deflection of the plate, that is given by 7. So for the analysis, it's very important to know mx and my formulas in terms of either curvatures, or most of the time we write in terms of the deflection W. Okay, as we know that we are considering W as a deflection, and we know that the differentiation of that deflection with respect to any parameter, we call it as slope, and when you differentiate one more time, we call this as moment. Okay, and if you want to differentiate one more time, that is third time, then there what we are going to get is shear force. Okay, so this we need to know. So equation 7 is responsible for this one. Now after this, we are going to follow some assumptions, small assumptions, and then we will try to reduce the form of the equation. Okay, now coming to here, now we have seen here, for example, in the mx equation or my equation, if any of mx or my is 0, okay, so mx or my is 0. For example, let's consider the first case when mx is 0. When you substitute in this equation, mx is 0, so you are going to get dou square W by dou x square, that is equal to minus nu into dou square W by dou y square. Similarly, when my equal to 0, we are going to get dou square W by dou y square equals to minus dou square W by dou x square. So you are going to get the equations like this. So, and we can clearly know from this equation that these are two curvatures, and you are getting a negative sign. So it shows that the plate has curvatures of opposite sign. So from these equations, we are going to draw two definitions. That is, a surface possessing two curvatures of opposite sign is called as anti-elastic surface, and as opposed to the synelastic surface, which has curvatures of the same sign. So if both the curvatures are of same sign, then they are called as synelastic surface. And if the curvatures of opposite sign, then we are going to call it as anti-elastic surface. And also we can take another assumption that if mx equals to my equals to m, substitute in this equation, and then we are going another assumption that 1 by rho x equals to 1 by rho y equals to 1 by rho, and when you substitute in the equation number 6, mx is considered as m, that is equals to d, 1 by rho x is considered as rho, plus nu into 1 by rho y, also we are assuming it as rho. So what we are going to get here, d equals to, we can take rho common, we are going to get 1 plus nu. So we are going to get m equals to d by rho into 1 plus nu, that we are going to replace, and when you rewrite that equation, you are going to get an equation 1 by rho, that is equal to m by d into 1 plus nu. So this is what the final result of this particular derivation. 1 by rho that is equal to m by d into 1 plus nu. So in the examination you may be asked the straight away question, consider the case of pure bending of the thin plates, and straight away he'll ask show that 1 by rho equals to m by d into 1 plus nu. Then you have to understand that the thin plate, when they are subjected to bending, the two moments are considered, mx and my, and then two moments induces stresses sigma x and sigma y, and then you are going to develop the equations for sigma x and sigma y and followed by mx and my. And finally with some assumptions like mx equal to my equals to m and 1 by rho x equals to 1 by rho y equals to 1 by rho, we are going to develop this equation 1 by rho equals to m by d into 1 plus nu. Okay, so that's all from today's class. Let's see in the next class with the next session, that is thin plate subjected to bending and twisting. Thank you.